So, hello, dear participants. I'm going to show our chemistry in benzofuran and indole synthesis. So, there are plenty of natural benzofurans and indole products. They're well known. And also, I want to admit that there are many drugs based on indoles or benzofurans course. And in our research group, we are interested in cyclohexenone chemistry, and there are two convenient ways to transform their aromatization. In this way, we can obtain benzene ring and modify some functional groups. And cyclization aromatization approach, which can lead to fully aromatic compounds or particular aromatic compounds. And especially we are interested in cyclohexenones bearing double and triple bonds. Synthesis of these cyclohexenones is quite simple. It's Robinson type annulation reaction. We can obtain desired cyclohexenones by condensation of mannich salts and two substituted acetoacetic esters. As you can see, yields in this reaction are quite good, and even sterile substituted cyclohexenones or TNL can be obtained. That was quite surprising for me, because reaction conditions are quite hard. First of all, we tried to employ allele substituted cyclohexenones in iodine promoted cyclization reaction. We started our investigation from heating of cyclohexenones with iodine in isopropylic alcohol, and we obtained 2,3-dihydrobenzofurans for AF in great yield, 83–91%. It's partly aromatic compound, and further transformation can make it fully aromatic. We use potassium hydroxide in isopropylic alcohol to eliminate hydrogen iodide and obtain corresponding benzofurans 5 in great yields. Also, we can perform nucleophilic substitutions. We used sodium azide for showing this possibility, and product 6 can be obtained also in probably 70% yield. It's not written here. Quite unexpected for us was elimination of hydrogen iodide from 2,3-dihydrobenzofuran bearing nitro group. It is well known that heating of aromatic nitro compounds in alcohols lead to azoxy compounds, but we changed solvent to dioxane, and still this process took place, and the only product we obtained was azoxy product 7. It was just a 37% yield, but we didn't obtain product 5D at all. The second advantage of using cyclohexenones is probability to construct indole core. And we use propargyl substituted cyclohexenone to obtain these structures. We started with heating cyclohexenone 1H with paratoluidine in the presence of catalytic amount of acid. And after a few hours of heating, a desired reaction took place, and we obtained mixture of 4,5-dihydroindole and fully aromatic compound 10. I should say that a number of catalysts was examined to be efficient in this transformation, and the best one was boron 3-fluoride eterat, which can catalyze this transformation very well, and we obtain desired product after 5 hours of refluxing. So after we found out that this reaction works, we were interested in aromatization process, and surprisingly, it was not so easy to oxidize dihydroindoles into indole, and we tasted some oxidizing agents, but the most suitable was air. We mobilized our mixture of dried products on the silica gel, and after 24 or 30 hours, it will completely oxidize. On this slide, you can see primary amine scope for indole synthesis. I should admit that only limitations for these procedures are nucleophilicity of primary amines. Amines with electron withdrawing groups, such as nitro group or pyridine ring, they can't react well on the first stage, and yields are really low. Also, we tested some cyclohexenones in this reaction, and desired indoles were obtained in moderate or good yields. So that works quite well. And taking into account all above mentioned results, we proposed reaction mechanisms that involve starting nucleophilic addition of amine to a carbonyl group of cyclohexenones, giving rise enamine 11, further transformation of enamine, its 5-hexadic cyclization give us this product with exo double bond. Its isomerization can give 4,5-dihydroindole, and further oxidation on the air give desired indoles in a quite good yields. So in summary, we have investigated a few synthetic methods for constructing benzocondensed rings, and I can say that these methods are quite simple. Starting materials are accessible and cheap. It doesn't need any transition metal catalysts or some very complicated workup procedures. So thank you for your attention.
Thank you very much for your presentation. So, have you questions? Please.
We can ask one question about try to cyclize something. You obtain dimer. Remember
Mm,
that with potassium hydroxide, previous slides,
elimination or
previous,
condensation?
go back,
Condensation.
still go back.
No,
Yeah, still
there
go
is no
back.
potassium hydroxide.
Still go back. Maybe I saw something wrong. Go back one slide.
Back?
Back.
No.
Maybe go forward. The molecule,
The-
the bond, nitrogen bond was formed.
Oh, with nitro group.
This one,
Yeah.
yes, this one slide. What happens here? Because the reaction condition is potassium hydroxide and dioxane, but here is what I see is now I can see the iodide, alkyl iodide served as a reducing agent.
Probably that's not
what
true
was-
because we did some experiments to confirm that we added potassium iodide and it didn't work. So
What was your hypothesis? What happened here? How this molecule 7 formed?
actually, we are not sure. Probably it's intermolecular
But it's a redox
redox
reaction.
process because potassium iodide cannot act as an reducing agent. So, and we changed alcohol to dioxane. We have even an idea that dioxane can contain some impurities of alcohol, and we checked it, but no, it didn't contain anything. It was
Okay.
pure.
Okay,
So it's
thank-
quite intricate transformation, I think.
Okay, thank you very much.
Another question?
I'm sorry, can I ask?
Yes, of course.
No.
Hello, my name is Yana and I have one question. Can you explain, please, how does the placement of the same radical in different position could play role on affect biological effect?
What? I'm sorry. Are you asking about biological properties?
Yes.
That's a problem for me because I'm chemist and we focused on creating cycles, but not on their properties. I just don't have this all collected data in my mind.
Maybe you have some guesswork how it could play on biological effect, different, the same radical on different places in structure.
Yeah, I can understand you, but I suppose it's almost impossible to predict it just in
Thank
a
you.
conversation. There are many books written about indoles and their biological activities. So,
Thank you.
Thank you very much. What do you intend to do with this set of compounds? All of them are selected, will be tested for biological properties. I have not.
we tried to test some of them for antimicrobial activities, but they showed not so good activities. And actually, biochemists said that small molecules, it's just nothing. They need to complex with protein to make it effective for drug discovery. So we have to think about special protein which can transfer it into a target cell, for example.
Only this intention, yes? No other.
Yeah, I think so.
Maybe you have some other idea how this compound can be used in your further studies or something else?
Yeah.
No idea. Only testing.
I don't have any ideas right now.
But it is in principle Some of them are really very interesting for continuation of this project, or not? What you think about that?
Yeah, for biological studies, our biochemists are interested in fragments bearing hydroxyl groups and pyridine rings, but I told you that we can discuss it with biochemists
Okay,
and for confirm these properties and continue these studies.
thank you.